Communication of technical information is an important skill for engineers and scientists to possess. In this lecture, we will discuss how to use graphical communication in a concise and efficient manner to communicate technical data to a general audience. We will briefly look at the history and development of different graphical formats, followed by a brief discussion of the purposes and attributes of good graphical communication. We will also look at different types of engineering graphics in common use. Then we will look at common ways that graphics are used and abused in popular media. And finally, we will look at ways to format graphics to convey information accurately and concisely. Some of the earliest graphs were depictions of the motions of natural objects, such as heavenly bodies, as functions of time. The figure below is from an unknown artist of the 10th century and shows the positions of the sun, moon, and planets over the course of a year. Similar depictions were uncommon in that era and did not recur for 8 centuries. In the early 19th century, scientific and economic data were often tabulated, but it was gradually realized that important trends in data were more easily recognized with visual graphics. Very often, economic information was depicted with bar plots of categorical information or scatter plots of data changes over the course of time. William Playfair was an early pioneer of graphical communication. Though he was an apprentice of James Watt, who perfected the steam engine, Playfair's focus was on economics, such as his famous plot of the price of wheat versus the cost of labor for over 2 centuries. An example of life-saving graphics is shown by the physician John Snow's map of cholera outbreaks in the mid-1800s. The black dots show mortalities from cholera in a London neighborhood before the recognition of bacteria as a cause of disease. This figure clearly conveyed that there was a problem with a local water source. It can be enhanced with a more modern contour that correlates outbreak severity with proximity to the well pump. Another life-saving plot was introduced by Florence Nightingale, a statistician and founder of modern nursing. Nightingale introduced the polar area chart to depict causes of death of British soldiers during the Crimean War. Her assessment of causes of death revealed substantial losses of soldiers by diseases like typhoid and cholera rather than war wounds. The information led to improvements in sanitation and ventilation and thereby saved many lives. Graphical communication is superior to tabulation of data for many reasons. It allows us to more readily observe broad trends in raw data and facilitates reasoning over such quantitative information. It can concisely summarize large data sets and make it easier to analyze data. Graphical techniques also allow several variables, such as statistical trends or thermodynamic information, to be depicted in 2- or 3-dimensional plots. Because good graphical techniques are so critical to engineering and science, it is imperative that great care should go into their composition. Scientific graphics, and all graphics for that matter, should be portrayed in as clear and unambiguous a way as possible. They should be drawn concisely so that only necessary information is presented without any extraneous data or artistic embellishments. The data, format, axes, and labels should be selected to depict the information as correctly as possible, with no ambiguities and minimal room for interpretation. Data should be presented as completely as possible for a selected experiment or survey, including any anomalous trends that may be inexplicable yet yield insights into objective phenomenon. Finally, graphics should be depicted conveniently with concise labels, logical formatting, and minimal need to cross-reference acronyms or read supporting text. Over the course of education in engineering, math, and science, you become familiar with a diverse array of graphical formats. Certain formats are better than others for specific data types and are preferentially selected to convey technical information in engineering subfields. Scatter plots and line plots are 2 important plots that often appear together but serve distinct purposes. It is useful to recognize when to use one, the other, or both in presenting technical information. Scatter plots should be used when presenting experimental or measured data, discrete data points, or calculations at a specific point. Meanwhile, line plots are used to depict theoretical equations that model a scientific phenomenon. They are also used to illustrate a line of best fit for experimental data. For the most part, scatter plots and line plots should be restricted to the above uses. If you use lines to connect experimental data, your colleagues may ask, is that the theoretical equation for the measured data? If so, can you provide the coefficient of determination? However, occasionally, lines may be used to help guide the eye in cluttered or disparate data sets. The figure below is a combined line and scatter plot that shows the variation of viscosity of a silicone fluid as a function of pressure at 3 temperatures. Note that the figure is on a semi-logarithmic plot, linear on the x-axis and logarithmic on the y-axis. The author also omitted extraneous pressure listings on the x-axis and used a reduced or dimensionless viscosity on the y-axis to save chart space. Furthermore, text boxes are used to indicate temperature rather than a legend. The bar chart below depicts available manufacturing methods for 4 families of materials, namely metals, ceramics, plastics, and composites, shown in economic batch sizes. Note the use of a logarithmic scale to concisely convey information over several orders of magnitude. Secondary axes are also helpful to depict dual units, such as those of the English and metric system on a single figure. Secondary axes and non-dimensionalization are often used to reduce the number of figures needed to convey information to an international community. 3 dimensions are often helpful to depict multivariate data, and the perspective that they provide can be helpful in giving presentations. Supplementary data, such as shown in the blue text at the bottom, can enhance a presentation to ensure that all relevant variables are depicted. However, 3-dimensional figures are generally discouraged for technical publications unless the author can demonstrate an inherent need and the ability to provide an unambiguous perspective. Very often, 3-dimensional data should be converted to 2 dimensions for technical publications. The figure below shows the preceding figure from the top view with labels to indicate important features, such as the upper plateau associated with the high coefficient of determination. The figure below is further simplified for publication by removing extraneous data ink and the use of distinct labels to clearly and concisely convey the important features of the plot. Note the use of dotted lines to show an important intersection of the x and y axes. Text boxes are also included to indicate the test conditions as well as the meaning of lines on the plot itself. This figure is less detailed than the 3-dimensional figure shown previously, but much preferable for technical documents. Several rules apply to the generation of good, scientifically approved graphics. First and foremost, show the data and avoid distorting what the data says. Any effort to mislead or misrepresent information should be detected by peers and experts in the field and may serve to discredit an author. One should also endeavor to present large data sets in a small, concise, and coherent space. The graphics should encourage the eye to compare different data sets and reveal as much data as possible for publication. Finally, figure captions and document text should be closely integrated with the figure to ensure maximum clarity of information. The following figure abides by the preceding principles in showing measurements of thermal conductivity of copper taken at several temperatures by several laboratories over several decades. It concisely depicts a large data set, uses balloons to credit measurements, and encourages visual comparison. Unfortunately, not all graphic designers abide by principles of clear, concise, and correct data transmission. Many news organizations endeavor to spin graphical information for political shock or entertainment purposes. Edward Tufte provides many such examples in his book The Visual Display of Quantitative Information and defines a lie factor to quantify the level of deception using a ratio of the exaggeration of a certain effect to the actual effect as shown in the data itself. Many media exaggerations focus on things like fuel economy and petroleum prices. The following figure shows the increase in mileage of automobiles from the mid-70s to the mid-80s. While mileages increase from about 18 miles per gallon to about 27.5 miles per gallon, or about 53%, the scale of the graphic increases about 783%. The quotient of the two percentages gives a lie factor of about 14.8. This is of course bad form for practicing scientists and engineers. Another example depicts the price of oil throughout the 70s using an exaggerated volumetric dimension to depict a linear change. The increase in cost is about 454%, while the increase in height of the barrels is less substantial. Meanwhile, the increase of the volume of the barrels exaggerates the change, giving a lie factor, based on barrel volume, of about 9.4. Another misleading practice of graphic designers in the media is the failure to account for inflation. Most people are aware that the value of money changes over the years, so any depiction of costs or prices over time must account for inflation using standardized monetary values, often the gross domestic product. The figure below shows state budget expenditures over the course of a decade in nominal unit dollars instead of inflation-adjusted money. The graphic designer evidently endeavors to exaggerate the state expenditures to dramatize the data. The plot also contains unnecessary embellishments such as the dimensions of depth given in the bar chart. The following figures provide a more scientific depiction of the price of oil through the 1970s. The graphic designers depict both nominal prices and inflation-adjusted or real prices to avoid misleading the public. While embellishments and an inconsistent scale remain on the right-hand figure, the figure is less deceptive overall. The graphic below has a combination of honest and misleading information. It intends to convey the need for additional funding for engineering research and development because the number of engineers is increasing while the funding is declining. While the title is strictly true for the last 2 years depicted, the earlier data contradicts that information. If we look at the data over 12 years, we see that the number of engineers has increased by 1.41, while the funding has increased by 1.47. Thus, the data contradicts the intent of the article, which argues that per capita funding for engineering research and development has decreased. Another misleading facet of the graph is that the 0 point of the number of engineers shown in the blue columns is far below the graphic border, while the 0 point of the research and development funds in the green columns is within that border. However, the graphic designer did use constant 1987 dollars to account for inflation and thereby accurately represents the true cost of the work. Edward Tufte gives 6 rules to avoid deceptive graphical practices. First off, numerical data should be directly proportional to the numerical quantities represented. If we think back to the highway graphic showing increases in vehicle fuel economy, we can see the breach of this rule through the exaggeration of highway width in proportional to the increase in mileage itself. Second and third, clear labeling should be used to defeat graphical ambiguity. Furthermore, data variation, not design variation, should be emphasized. The preceding slide gives one example of where the graphical designer failed to ensure that the origins of the two parallel axes, represented by the bar charts, coincide. The number of information-carrying dimensions should not exceed the data dimensions. The example of the oil barrel slide showed the use of 3D design variation to exaggerate data variation. Time series displays of money should use deflated and standardized units of money rather than the nominal values for a given year. We saw this in the price of oil plots that used inflation-adjusted money based on the gross domestic product to show their data. Finally, do not quote data out of context. Any efforts to obfuscate data when detected by your peers can be a career-ending activity. Tufte also distinguishes data ink from non-data ink in making concise graphics. The figures below show actual voter registrations on the x-axis versus predicted registrations on the y-axis for 104 cities in the year 1960. The figure on the left has excessive non-data ink from the dense grid lines that overwhelm the actual data points. The middle figure has insufficient data ink, only showing the trend line from the measured data as opposed to the actual measured data points themselves. Meanwhile, the figure on the right has the right balance of critical data ink and necessary non-data ink to put it into context. Nothing extraneous is listed, all of the measured data points are shown, the line of best fit is shown, and the information is conveyed without use of excessive ink. The figures below show the atomic volume of several elements as a function of their atomic number. The figure on the left has a border and tick marks that are regarded, at least by Edward Tufte, as extraneous non-data ink. These are isolated in the middle figure for the time being, which when removed show a better graphic replaced in the middle that focuses more on the relationship between atomic volume and atomic number for the element shown. And the freeing of space by removal of the non-data ink allows one to add more data ink to the drawing, such as the labels of sodium, potassium, rubidium, and whatnot in the figure to more carefully distinguish what exactly the graph is trying to convey. The preceding figures illustrate 5 rules to optimize the presentation of data with respect to the ink used in the figures. Above all else, show the data itself, maximize the data ink to non-data ink ratio, erase all extraneous non-data ink, erase redundant data ink, and revise and edit the drawings to minimize the amount of unnecessary ink used by publishers to publish the figures themselves, and yet concisely and clearly convey the information that is intended to be presented in the figures themselves. For centuries, graphics were made by the graphic designers by hand. Meanwhile, in the recent decades, graphic software packages have become available that allow one to present graphical information in a much more concise and speedy manner. Most of us are familiar with software packages such as Excel, MATLAB, and MathCAD. Meanwhile, a range of additional software packages are available such as Origin, Descartes, Chart Director, and Grace. Many of the preceding softwares have default settings that are usually wrong and require readjustment or resetting by the graphic designer themselves to ensure that it meets the formatting expected by their professional organizations. So the titles defaulted to on many of the plots in Excel often have the wrong font size, or at least in relation to the size of the figure itself. Very often the axes labels and units have erroneous font size, font type, and the range and increments used on axes units have to be reset by the user to ensure that it covers the necessary range without going beyond that range unnecessarily. Axes types are usually defaulted to linear axes, but sometimes you need semi-log plots or full logarithmic plots. And also axes grid lines or tick marks may be set inside or outside. You may have a full grid system with a lot of unnecessary non-data ink, which should be removed to meet the guidelines outlined by Edward Tufte previously. Likewise, the legend key, font size, type, descriptors, and whatnot are very often wrong as well. And also the background, border, and aspect ratio may not be quite the recommended shapes and configurations for the publications that you aim to present. I very often recommend a white background because typically in the case of technical publications in Word format, it's useless to have a colored background because that represents, in Edward Tufte's terms, extraneous non-data ink. And similarly, a white background in PowerPoint is the safest default for anyone who might request to use your graphical representations in presentations of their own. And likewise, formats differ between papers and presentations. In papers, you generally don't use a title. Meanwhile, you do make use of a caption, as opposed to presentations where often a title can be handy, but captions are generally undesirable. Likewise, legends versus labels differ between papers and presentations. I'll show you some of the recommendations for papers in a forthcoming slide, or set of slides, and the use of labels also also allow one to forego the use of excessive keys and the following series of slides is based on my own experience with optimization of graphics. The data is based on the film thicknesses that are generated by different oils in a typical ball bearing. It illustrates the many formatting changes that are necessary to make scientific graphics that are acceptable for publication in engineering journals. When I graph the data in Excel scatterplot, I obtain the default graph shown. The forthcoming slides show all of the changes needed to be accepted for publication by the editor of the journal to which I submitted the manuscript. First, I changed the axes from linear to logarithmic scales. I also set the range of the x and y axes to cover the useful range of data. Next, I reformatted the axes to omit extraneous decimals or so-called non-data ink. The figure at the upper left shows extra decimal places on the x and y axes, while the figure at the lower right shows that they've been removed. I also made effort to distinguish experimental data from theoretical lines to ensure that there was no confusion as to which type of information was being presented. Afterward, I labeled the axes and listed the appropriate units for each axis. I also commonized the font size and weight throughout most of the figure. Then I made the theoretical lines black and distinguished the experimental data markers into triangles, diamonds, and squares to avoid confusion if it were published in black and white. I also added the border and moved the legend within the border. Next, I omitted the title, which is more non-data ink in technical publications. I also removed the legend and replaced it with text boxes and arrows to make it more concise. I also removed excess data at the intermediate temperature of 348 Kelvin because it was too cluttered and could create confusion. A comparison of the initial figure to the final figure illustrates the collective improvements made by the reformatting. The much improved figure on the lower right shows the linear relationship between film thickness and entrainment speed. It properly uses lines for theoretical data and distinct points for experimental data. Most non-data inks, such as the grid lines, legends, and titles, have been removed as well. Thereafter, I simply copied and pasted my template figure for subsequent plots, rather than repeating all of the preceding formatting processes every time I needed to make a figure. However, I still had to plot new data, relabel axes, reset ranges, and so forth, though I saved a lot of time by meticulous formatting and ensuring that I had a correct and acceptable format the first time that I made these Excel plots. An often debated feature of graphical presentation is the aspect ratio of the figures themselves. Many people agree that a larger base than height is generally preferable in graphical presentation. However, artists and architects have hypothesized that an ideal ratio exists for optimum aesthetics. This ratio is referred to as the golden mean or the golden rectangle, an idea that originated in ancient Greece and has an interesting history and mathematical basis to it. It can be found by a solution of the equations of ratios of height to width as shown below. However, many people contest that the golden ratio is subjective and is equivalent to a number of similar ratios depicted by the mathematician G.D. Birkhoff in the figure shown there. So whatever your perspective is on the aspect ratio of graphical presentation, I myself have found that it is beneficial to use that ratio, or at least certainly not detrimental, but nonetheless I'm sure that it's not a showstopper for any of the graphical representations that you yourself may submit. Graphics should avoid relying on the use of colors as much as possible. Very often your PowerPoint presentations or technical documents may be printed and distributed in black and white, so any color designators would be lost to the persons reviewing the work. Even if a color printer is used, it may run out of ink or certain pigments and thereby mislead the reader. For example, if you specified green for a certain label and yet you ran out of blue ink and the label turned out yellow, the reader may misunderstand what exactly it's trying to convey in the text. And finally, a significant proportion of the population is colorblind. You've probably heard of red-green colorblind, and may find your color selecting confusing or even inconsiderate. Figure captions should supplement the text of a technical document and/or presentation to be sufficiently explanatory to allow competent researchers to replicate the results shown by the author. The figure caption below provides specific details of the experimental settings of a nuclear magnetic resonance device in terms of frequency, solvent type, and temperature to allow researchers to replicate the results shown in the figure. Also note that all figures taken from another source should be properly cited. Even self-citation should be used to ensure that readers or viewers can locate the source of the information provided. Edward Tufte provides a nice summary of the preceding information in his outline of friendly versus unfriendly graphics in his book, The Visual Display of Quantitative Information. As we covered, abbreviations or codes should be avoided in friendly graphics, whereas unfriendly graphics tend to rely on abundant abbreviations or acronyms. Words should run from left to right as opposed to running vertically. I actually do often contradict this because I think vertical labels on the y-axis aren't that problematic, but nonetheless I will repeat Tufte's advice as shown here. Small messages should explain the data. I like to use text boxes with arrows to provide some insight onto the graphics themselves. Labels are placed on graphics so that no legends are required, even though legends are a default setting in Excel and many other graphical software. Shadings and colors are to be avoided, namely because photocopying or scanning devices may be black and white, and likewise certain people tend to be colorblind. And unfriendly graphics, of course, ignore that advice and tend to go with whatever the author suggests or infers is most direct. Type should be clear, concise, and modest, and a mixture of upper and lower case is advised as well. One might think that all capital or all small letters would be just as good, but it has been found that readers retain information better and distinguish data better when a mixture of upper and lower case data is used. And likewise, type should not be overclouded or overbearing that uses redundant, unnecessary, non-data ink and more or less presents kind of a sloppy hodgepodge of information on. I hope that this summary of the history and purpose of graphics has been beneficial to you. While the many types of graphics should be familiar after all your years in engineering, math, and science, you should be able to recognize how to make graphics as clear and honest as possible through a review of the proper use and abuse of graphics. I hope the rules of graphical presentation and a review of the examples will allow you to make clear, concise, correct, complete, and convenient graphics to support your academic work and your future career. Finally, I would like to thank Dr. Yip-Hua Chung for detailed advice on the best practices in graphical presentation and formatting from the perspective of a journal or book editor. And likewise, I'd like to thank Dr. Lynn Schlager for the valuable reference material, namely Edward Tufte's book, and his preliminary formulation of this presentation, references which I had used repeatedly throughout this presentation.